So thanks a lot for the invitation. Very excited to be here in India. Hope to come back many times again. So thanks a lot for Ravi for making this visit possible. So I want to take the opportunity to discuss some joint work with Jose Rafael Correa from University of Chile, Niloy from BU Amsterdam, Alberto Vera, who was a master level student at University of Chile when we did this work, and is currently a grad student in Cornell. You're bothering me already? I mean, I had to.
This button and later we can just put this button.
Okay. Now, Ravi is okay? Okay, good. I can. Okay, so you kind of know the story by now. You have a whole bunch of nodes. You can assume they're agents, they're people, they are clients, customers, they're mobile devices. And for me, I'll talk, this nodes, I'll refer to them as nodes. These nodes can interact. Some of them have something like some information, like a rumor, and I just refer to them as being active, and then there's some interaction going on, and sort of the rumor spreads, or activation cascades through the network, and you're interested on something, whatever, the time everyone gets activated, or a target set gets activated, or some significant fraction of the network gets activated. And this kind of situations have been studied in many contexts. You've already heard a couple of them. Let me mention some others. They're in the literature, you find them as it's called sometimes rumor spreading social networks. And the rumor is something very general. It could be, say, some software update that is being spread, or some adoption of a new technology. You heard about epidemic models. It's also studied under the name of viral marketing. Some people are initially targeted for a special marketing campaign, and the idea is to have it to kind of take advantage of the dynamics of the social networks in order for this marketing campaign to propagate throughout the network. And the setting that I'll be most interested on is something has like network theory, people call it like communication offloading in opportunistic networks. I'll describe in a minute what exactly I mean by that. So it's okay, Ravi? Or? Okay. Okay, so let me just stress something that is quite obvious. Models really differ a lot depending on how the situation differs a lot depending on how you model interaction and communication between nodes, even, things like how you model how time evolves. Just to drive the point through, and it will help me in some of the things I'll be discussing. So here, what I'm trying to illustrate is a network. Each square represents a state of a network. There are 256 nodes. It's a 16 by 16 square. Time evolves in discrete time steps. Initially, there's only one active node, and sort of the way these nodes it's a very homogeneous network here, and the way they interact is that at each step, an active node randomly chooses another node in the network, establishes a communication, and if that node chosen was inactive, now it becomes inactive. So what you can see here is going on is like kind of what you expect initially. There's an initial phase where kind of the number of active nodes sort of doubles, and there's an end phase where essentially the number of inactive nodes kind of decreases by a constant fraction per step. And then there's an in-between regime where things, the number of active nodes grow smoothly, and the number of inactive nodes decreases smoothly. And so let me consider a somewhat different setting. And here, time evolves asynchronous, time is continuous. And the situation now is that each pair of nodes will interact at some intervals of time, and this is independent of what happens with other nodes, and the intervals follow some exponential distribution, okay, of some rate, and the rate is done in such a way that it's chosen here, so in average, each node interacts in 1 unit of time with one other node of the network. And then I've taken some snapshots. Huh? No, every pair in they interact with some at some intervals that depend on just the exponential distribution. Okay, so and then I've taken snapshots and show the state of the network. So it's a bit different. Initially, things go pretty much as in the previous case. Sort of things kind of increase at a very steady state. There's an end phase that the inactive nodes disappear at some constant fraction, but then the in-between stage is much shorter, okay? And in general, asynchronous models makes much more sense if you're modeling interaction in social networks, but the synchronous models have been studied much more. It's probably because also this one's a little bit harder to handle.
The number of attempts to infect conserved in the model?
Sorry?
The number of attempts to infect, like in the discrete model, it's clear how many times. In the second model, could you scale the mean of the exponential distribution in such a way that the number of attempts would be the same?
Yeah, that's what I tried to set it. So the rate will be at which they will, a node will meet another one will be kind of the same and sort of comparable. Now, what is an opportunistic network? Well, people in the network community have realized, a lot of the social networks, agents are kind of mobile, and when they get close to each other, you can use this opportunity to exchange content and information and offload traffic from a very congested network. So you have a very congested cellular network, and think of this as some service provider, and all of this are its clients. They pay a flat fee to the service provider. He gives them some content, and the thing is that he has to pay the cost of pushing the content through the cellular network, which is expensive. So gives a better deal to its customers if they're willing to sort of share the content once they interact by interacting between each other. So I'm interested in kind of that setting, but where there's a fixed deadline scenario. So the content has to be distributed. Every customer has to get the content by a fixed deadline. So essentially, you can think of this as a quality of service restriction, or maybe just that the content, the information that is being distributed, some traffic information, whatever, it's obsolete after some deadline, or you're offering a product that is some flight or some tickets for an event, and once the deadline passes, it's worthless. So then the thing is the problem is what should be the strategy of the content provider in order to minimize its cost. Okay, so this has been studied in using some artificial data and also some real data. And then some mechanisms have been proposed to kind of strategies for the service provider to use. And this group of people sort of told us about the problem. Their analysis is not really very rigorous, or no, rigorous is not the question. They cannot give a clean analysis of what is going on. So that was kind of the initial motivation, and really mathematically it's quite interesting. even simple cases, and that I'll tell you about, although they're not very realistic, the simple cases that we can analyze. So to be completely precise, we have n nodes. They can meet. Once they meet, if one of them is active, the other one becomes active. Time evolves in a continuous fashion, and specifically, the interval between two interactions of a pair of nodes follows some exponential distribution, which is something with a rate lambda over n, and it's the right normalization, doesn't matter too much. And this exponential distribution, if you're not completely familiar, it just follows some density function like that. You know, the higher the rate, this is a higher rate exponential density function of an exponential. This is a lower rate, and the higher the rate, essentially the average of this function is smaller, okay? So there's this external entity that does pushes, and for those activates nodes, and it has to pay. We'll assume it's a unit cost. Opportunistic communications are just free, and the nodes, when they become active, they can signal this external entity that they became active. And there's a fixed horizon deadline. So there are two possible scenarios. One of them is like the external entity.
There's an underlying graph, and you connect to somebody else.
Yeah, I'll just assume the complete graph, and the questions are all concerning the more general case. Yeah, and a very homogeneous symmetric situation. Okay, but even this is quite challenging to analyze well. Okay?
So, what is the, from the designer standpoint, what are the choices to make? Because pushes have unit cost.
The quantity of pushes. So you want to minimize your cost, and at the deadline, anyone who hasn't been activated through opportunistic communications, then you have to inform them, and you have to pay the cost again.
And the opportunistic communications are not under your control. They are happening according to this random process.
To random process, and they're free.
But they're not under your control.
No, not under your control. Okay?
You have to pick which opportunistic one to take advantage of, when to do the push. But opportunistic would automatically do the...
Yeah, if one of them is active and the other one is not. Okay? So
what's the push doing? It's just going in and activating number of forces.
yeah, I just give the information to a couple of people, and then hope that you will interact between each other and propagate that information. So at the end, everyone will know the information, and you know, I don't have to
Push very beginning.
Of course, you have to push at the very beginning. The thing is how much you have to push at the very beginning, right? And there are two situations. One of them is you take like a hands-off situation. It's like I push at the beginning and at the very end, okay? How many, yeah, you have to decide at the beginning how many nodes you have to activate. Sorry?
So for example, if there is a source node, initially he decides that I have to do 10 nodes, 10 different other nodes. So that's what you are telling as equality, or how much?
How much, yeah. So if the network wasn't so symmetric, it would matter which nodes you're pushing the information to.
And what you think, it doesn't matter whether I'm more near to the source or it is part.
No, it doesn't matter. It's just, yeah. You just pay for using the cell. The service, the content provider pays for using the cell phone network, but then since the content provider knows which nodes are active and which are not, it can have a more hands-on strategy in which at some point, if it sees that the spread of information is going very slowly, it can panic and then push information to a couple more nodes in order to sort of bootstrap the process, okay? So there's this adaptive and non-adaptive scenario, and the natural question is, what is the price of adaptivity? So essentially, how do they relate? The optimal adaptive strategy against the optimal non-adaptive strategy, how do the cost?
Active case, what is that information?
So at every point, you know which nodes are active, because whenever they become active through some opportunistic communication, they just signal with a short message that they became active. So you know at every time. And you have to know, because at the end of the deadline, you will have to push information to whoever doesn't have them, has not become activated. Okay, so of course, there are other questions, right? What is the best adaptive strategy? What is the best non-adaptive strategy, and so on? And that is kind of related to the question we have. So bottom line, we showed that the adaptivity ratio between, the optimal cost of a non-adaptive strategy versus the expected optimal cost of an adaptive strategy is bounded by a constant. There's not so much to be gained up to constants. And so in plain English, you can take a hands-off strategy. Yes?
I mean, what's the constant?
Yeah. Well, that's part of my, okay.
I mean, I guess.
No, I understand the question.
The behavior of the opportunistic stuff is fairly well concentrated. For instance, it's fairly close to what you would get in expectation or from differential equations, things like that. Then, okay, the fluctuations around that are small, and you would have to be kind of lucky to take advantage of the fluctuations.
Yes.
But still, order 1 doesn't sound bad. 1 plus little o.
To make another, okay. So, I mean, numerically, so you have the right intuition what's going on. To make it precise, it's a bit more work, and the constants we get are not so good. Numerically, there seems to be strong evidence that this can be a 2, just a factor 2. But it's even worse. I mean, it could be that it's a small additive constant, the difference between the two costs. We really cannot give a precise enough analysis to get there. Okay, so but we were happy to get this at least. Okay, so the non-adaptive is kind of easy. I won't get into the hard part. It's just no time. But the non-adaptive is what you really look is at the time between consecutive activations when a new node becomes active. So you have I nodes, and then after some time there are I plus 1 nodes become active. And so how is that the time distributed? Well, it's the minimum of this number of exponential random variables. And why this number? Because there are I nodes that are active, and they can interact with n minus I inactive, and that will produce another active node. So, and it's known that the minimum of that many exponential random variables behaves like another exponential random variable with a rate which is much higher. Okay? So as you see, when there are few active nodes, rate is not so good, and then it increases up to when I equals n over 2, and then there's a lot of opportunistic communication going on, and then things start slowing down again. Okay, so when the rate is very high, essentially you have so you can predict, you have interactivation times between I and I plus 1, which is very small, and also the whole process is quite deterministic, as you were saying. Okay, so the parameter lambda really doesn't matter. I'll just assume it's 1 from here on. So here's a graph of how the rate goes. And here it's like you start with 1 point, and then I just generated the random variables according to how the rate is changing. And as you can see, a lot of it's going on like in the middle part here, and the spreading process is slower towards the tails, right? So one simple observation is that no matter what, in a non-adaptive strategy, initially, you're never going to activate more than half the nodes. It makes no sense to do that. So why, if you were activating more than half the nodes, every extra activation, you pay one, and then you are in a worse situation. I mean, the rate at which things are going to, information is going to propagate decreases. So it really makes no sense. I mean, it's better just not to activate more nodes. You can as well activate them at the end and take the advantage of the higher rate regime where a lot of opportunistic communication is going on.
Maybe I missed something. Doesn't that depend on when the deadline is? I mean, if the deadline is really soon, then it might push to everybody.
No, it never pays to push more than half. It never pays to push more than half.
Assuming lambda.
Independent of the deadline.
Oh, okay. There's no point in initially pushing one.
No, because you want to really take advantage of this high regime rate where opportunistic communication is really happening.
Oh, but when you say it's not performed more than n over 2 pushes, you mean initial pushes?
Initial pushes, yes. Sorry, yes. No, so both have the choice. Okay, non-adaptive, everything that is not active at the end, you have to push. Okay, you have to, because everyone has to be informed at the end. Now, the fact that non-adaptive doesn't do more than half the pushes initially means also that for adaptive, it doesn't make any sense to do it either.
That's because of the choice of lambda is 1.
No. It's independent of the deadline, independent of lambda, you will never initially.
Number 2 at the beginning.
Yeah, never. It doesn't make, okay. And neither of any of these strategies. And essentially, what will be the optimal strategy is the optimal strategy, non-adaptive, will depend on the deadline. And so what do you want to do? You want to take advantage of this, the part of the regime where opportunistic communication is really going on, right? You don't want to miss this part. So you don't want to start very early, like with very few active nodes, if your deadline is small, because opportunistic communication will kind of be slow in comparison to what you could get by being here. So if you start with very few, you will get a couple more nodes, but then you will have to pay a whole bunch at the end. So it doesn't make sense. So really what you want to do is sort of start somewhere where the expected number of nodes that you will have to activate at the end is kind of the same. Okay, so it's kind of and formally you get you can think of. I have a non-adaptive strategy. I can think of the number of nodes that it has activated up to time t. I'm interested on this cost. The cost is the minimum of the number of initial activations. And here the notation is kind of confusing, but this thing is the number of expected number of uninformed nodes at the deadline. And it's better to think of this as a function of some t. And it's kind of funny the way the function is defined, but so you have a deadline, which is tau. There's some initial activations, but at time t, I'll condition on the fact that k sub n of t equals k, and I want to define a function that tells me, if at this time I have this number of active nodes, what is the expected number of inactive nodes at the deadline? Okay, that's this function, and formally is this thing over here. And you get that this function is convex by some submodularity arguments. Those are not hard, which means immediately that this other thing has a unique minima, which the intuition says it should. And as Chris pointed out, at least, when there are lots of nodes being active, this differential equation kind of models the spread of information. This is very similar to the model in the previous talk. When there are not so many active nodes, you have to work a little bit harder and show that the solution to this differential equation actually still is okay, and you get like, the function is this, and here now it's easy. You can just optimize for the optimal k, and you get exactly what the intuition predicts, that the cost is double the number of initially informed nodes, and it's sort of this form. So nice, you can get everything you want, well describe what is the best strategy for the optimal, for the non-adaptive strategy, how many nodes you have to initially activate. So, okay, so from here you get like, if tau is like twice the log of n, this kn is like a constant, so the cost, the non-adaptive cost is like a constant. Since the adaptive cost is at least 1, you have the bound for this very trivial case, all right? For the case of small deadline, I'll skip this. If the deadline is small, you want to capture that you are in the regime where there's a lot of opportunistic communication going on. So the rate of communication is very fast. If the rate of communication is very fast, because what I showed before, really there's very little randomness going on. The process is very kind of deterministic. Deviations are very small. So essentially, a non-adaptive strategy can predict as much as an adaptive strategy. And there's a nice coupling argument to make that formal, and you get the bound. And really, the complication is in this regime. Okay, not hard to figure out that the best adaptive and non-adaptive strategies, really, there's some numbers that are relevant. Like for the non-adaptive strategy, you can think of like, if the deadline is this length, then I'll push this many. If the deadline is larger, then I push fewer initially, and so on. So then there are some parameters like this. And for the adaptive strategy, there's also some important like thresholds where, if time is running out, I better activate more nodes. Okay? But it's very difficult to characterize those parameters and get a handle on the adaptive strategy. So what we do, we relax this adaptive strategy appropriately. I'm running out of time, so I want to mention some questions. And then we have to do a whole bunch of transformation, define some martingales, dominate this by some processes. This is much more technical. I can talk to you if you're interested later, but let me mention some of the questions that I find. Okay, I'll skip this too. Okay, some of the questions that I find interesting is, okay, so we think the adaptivity ratio should be 2. And we're nowhere near proving that constant. It might be possible that the difference between the optimal non-adaptive strategy and the adaptive strategy is just a constant. We cannot, or even farther from proving that. It's kind of disappointing that we're considering a very homogeneous network. Social networks are not so symmetric. A broader question is, for which kind of graphs or families of graphs still this constant gap, the constant adaptivity, this bound on the adaptivity ratio can still be a constant, and a natural thing will be sort of expanded graphs and high conductance graphs. But then the more interesting questions I find will be, are assumed that to consider in homogeneous situations. So here there are three that might be of interest. So one is that the rates are satisfy some kind of triangle inequality. The other one is that there's some underlying geometric space, and the inverse of the rates are like, or the rates are sort of proportional to the distance between the nodes. And lately, a favorite object of another line of things that I've been working on is like, assume that your underlying graph is some hyperbolic random graph. If you don't know, read about them, they're fun. There's some hyperbolic geometry involved, but these graphs seem to model well social networks, some characteristic of social networks. So it will be very nice to have some results for this kind of underlying network. And the other reason why I mentioned this is that people who originally mentioned the problem to me, for this kind of networks, they're like these nodes that have very high degree. So it will seem that the content provider, one thing that will try to do is kind of push information, initially activate these nodes that are highly connected. But this seems unfair. So there are some notions of fairness which they didn't understand very well how to model, that are more game theoretic maybe, and I'm not so familiar with that topic. Yeah, sorry for that.
So time for one or two more.
Maybe someone else.
Yes.
There's someone else. Yeah, I prefer someone else. Yes? That was a map of a function, right? It's this.
So here, like, if I consider that uniformness and what is, let's say, the constant amount of pushing is happening from the beginning. So at the initial, at the start of the process, everything is success because whenever I try, I can make him active. But towards the end, I mean, you have more failed conditions. So this curve is like symmetrical.
So this curve is just the rate at which, if you look at this process that like each point is another node becomes, okay, and if you start with one, then there's the process, the interactivation time is is large. And when half of the nodes are active, then the interactivation time is really small. But when you move, then also again it becomes small.
Yeah, in that case, what I was expecting, like maybe towards the end, your curve should be like
Not symmetric. Which curve?
So this graph itself, this I lambda I graph itself seems like a perfect symmetric
It is.
inverted view. Is that really? Is this?
Yeah, but this
It seems like it'll double.
no. But here I'm just plotting this function, which is just the rate. Yeah, it's perfectly symmetric. Yeah.
It's plotting it as a function of I, not as a function of time.
Oh yeah, it's yes. Yeah, but it's I.